Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I hope, yeah.
All right, well, I'm pleased to welcome today Idan Spector, who is visiting from Bar Ilan University in Israel, where he's working with Ido Dagan on textual entailment. And he's just joining us from Yahoo Research, where he spent the summer working on textual entailment. And he's going to be talking to us about his dissertation work.
Oh,
Wow.
long to be, yeah.
Eventually.
Okay, so I'll talk about our ongoing work in the Bar Ilan group, given by Ido Dagan. And we're focusing on textual entailment. I'll talk about the framework as a whole, and then a little bit of knowledge acquisition that is probably needed for doing such kind of inference, and then the applicability of textual entailment for some NLP tasks. So let's take a look at the framework first. If you're looking at natural languages in a nutshell, we've got two fundamental phenomena that we want to handle. First one is ambiguity, when we have a surface form that could be interpreted in different meanings. If you're looking at the word acquire, it could be both in the meaning of buying something or learning something if you acquire knowledge. But we'll focus in this talk on variability, which is kind of in the other direction, where we have a specific meaning and we can express that meaning in many different ways in the language. Actually, if you think about it, variability makes a lot of NLP tasks hard. Because, for example, if you're looking at question answering, if we know that the answer will appear with the exact word as the questions, it will be very easy to find the correct answer. But the problem is that answers are expressed in many different ways, and we have to figure out which is the right one and the wrong one, and learn all these different ways to express it. And the same thing applies for many other tasks. For example, information retrieval. Again, if you have relevant text for a query, it could be expressed in many other ways than just the words of the query. Let's take a look at one example of variability. If you're looking at the phrase "Dow ends up," we can express that meaning in many other ways. We can say Dow gains 255 points, or Dow hits record high. And we want to model this kind of variability, and we want to capture it at the text level. Well, such kind of modeling already exists. That's equivalence. We'll say that two text expressions more or less convey the same meaning. They are equivalent. For example, if you're looking at Dow gains 255 points and Dow climbs 255, we could say more or less that they are equivalent. However, a more general approach or a more general model for that is that of entailment. Because equivalence is it's not a directional relation. But entailment is a directional relation. If you're looking at entailment, we want to infer the meaning of one expression from the other. For example, Dow gains 255 points entails Dow ends up, but not vice versa, because we cannot entail how many points it ended up just by saying that it ended up. And if you think about it, if we're looking at equivalence, we can look at it as two entailment directions, right? From the first expression to the second one, and the second one to the first one. And so we can think of equivalence as just a specific case of entailment. We can just measure the two sides, and if we have two sides of entailment, we can say that they're equivalent.
So how do you incorporate some other situations where the meaning-wise they are equivalent, but one may have more emotion, some other aspect of the meaning, which is not something that can be inferred?
Well, that's something. If you cannot infer it, perhaps the model is not sufficient enough for that example. That's OK. But this is something else. But let's talk about where we use such entailment inference. But first, let's take a look at that definition. What we define as applied textual entailment is that, of course, it's a relation. It's a directional relation between two text fragments, a text and the hypothesis. And we'll say that the text entails the hypothesis if typically a human reading the text would infer that the hypothesis is most likely true. So as we can see, this is an operational definition. We've got the most likely true. It's a bit vague. But if we think about it, it's how we humans actually perform inference. So that's what we expect NLP applications to provide us, to behave. We want them to perform what we need. Okay, so that's why we added humans look at things as most likely true. Another thing here is that when we, as humans, perform inference, we're using background knowledge that we have. Could be word knowledge, could be linguistic knowledge, as part of the inference. And so this definition captures also the fact that there is some background knowledge needed as part of inference, yes.
And so you don't require that the text actually has anything to do with the hypothesis. If the hypothesis is true to a normal human, then anything could entail that hypothesis.
That's true. Actually, if we want to play the game correctly, we would say that hypotheses that are actually true without looking at any text are not really interesting for us as part of entailment. You could just say that they're trivially entailed. So what we really want to have is that, well, if you want to infer whatever you can infer from a new or a given text and not just in general way. So that's more or less where you can put yourself in some kind of frame. So why do we want to use textual entailment? First of all, it unifies some semantic needs, some inference needs in many NLP applications. For example, question answering, multi-document summarization. And I'll give an example, a QA example. If you're looking at the question, what reduces the risk of heart attacks? Well, we can transform it into affirmative form and ask, well, X reduces the risk of heart attacks. And if someone will give us a candidate text with a candidate answer, like aspirin prevents heart attacks, we can take that candidate answer, plug it in our hypothesis, and then ask whether the text entails the hypothesis. And if there is an entailment, then aspirin is a correct answer. And if there is not an entailment, then it's not a correct answer. And that's how we can use entailment inference or entailment engine for QA. And the same trick can work for IE or IR and other applications. Another important thing is the fact that in the definition of textual entailment, we define it at the text level. So there's no inner representation that is enforced here. For example, people were thinking maybe that logical representation and logical inference is the holy grail of performing semantic inference. Perhaps it's true. But what we're saying here is that this is how to do it and not what to do. And like this is a bit changing the way to look at things. Well, textual entailment is what we really want to do. And how to do it? Well, now we can try a lot of different things. Perhaps logical inference is correct and the best answer. Perhaps there are other things that might be working as well. To encourage the research on textual entailment in the community, we've organized in the last 2 years 2 challenges, Pascal challenges called Recognizing Textual Entailment. In the heart of these challenges, we've constructed 2 data sets containing true and false entailment examples, so pairs of text and hypotheses that there might be either true or false entailment between them. And there was some kind of challenge between, well, competition between different research groups that provide their inference engines and try to figure out the results. And then there was some seminar. And actually, we thought that the 2 challenges were very successful. The first one, we had 17 groups participated, and the second one, we had 23 groups. So there's a large increase, and we've already been approved for the third one. We're preparing it right now. So of course, if you have an entailment engine, which I know you do, you're more than welcome to join also the third one. And as well, the organization of the last challenge was co-organized also by Microsoft and, well, other groups. Some examples from the last challenge to get the notion of entailment. Well, we've got, in the first one, for example, the hypothesis is strong sales for iTunes in Europe, and the text is iTunes software has seen lower sales in Europe, and here we have to understand that lower sales and strong sales are antonyms in order to understand that this is a false entailment. Probably a more interesting thing is to look at the last one. The hypothesis says Cardinal died in 93. And the text says a shootout in May 93 that killed the Cardinal. Well, we'll probably say that it's true, but it could be that the Cardinal was shot in 93 but just died in 94. But that's what we mean when we say most likely true. Because if we just given the text, we'll all say, yeah, it was probably, we can live with that. We are very happy with that conclusion that's referred to false. And that's what we want to capture when we say most likely true. There are probably other examples of different things we say most likely true. Some methods that were used in the last challenge for entailment inference. Well, the main approach was to try and measure the coverage of the hypothesis by the text, using lexical overlap, some lexical syntactic structure that could be matched, paraphrases that were used, some other global similarity parameters. One group tried to measure cross-pair similarity. You've got the data set, which is annotated, and you got a new pair. You can ask yourself, which is the most similar pair to that new pair that we can find that is annotated? And then we can just mark it as true or false based on the most similar one, like a nearest neighbor approach. Another approach was done by Microsoft is to directly identify mismatches to measure false entailment. Not just saying, well, I can't cover everything, so that's false, but just measuring, well, this is colliding, so there's a mismatch here, and that's immediately false. And of course, there was logical inference, as again we said, that could be still very good approach and probably maybe the best. 2 insights from the last challenge. Well, for the first time, we found out that deeper methods can clearly outperform shallow methods. In deeper methods, we mean deeper semantic methods based on syntactic levels and logical level of inference. And shallow methods are at the lexical or n-gram levels. But there are actually just 2 groups that manage to get that. And most groups still didn't manage to get over the lexical baseline that we calculated. And there are 2 points that were reported by different groups. First one is lack of knowledge base, world knowledge or linguistic knowledge. And the second one is lack of training data. That these are 2 important points that were kept repeating, especially the lack of knowledge, kept repeating on and on by different groups. There's just not enough knowledge and knowledge resources that you can perform good and robust inference. So we'll try and take a look at how to acquire at least part of that knowledge that might be needed. Something we called entailment rules. That's a work that we published in 2004 together with Hristo Tanev and Bonaventura Coppola. Well, the motivation, again, if you're looking at the question, what reduces the risk of heart attacks, transferring it in affirmative form, and then given a text, well, how will we perform that inference? It will be great if someone will give us this rule that will say, well, if you see X prevent Y, you can infer that X reduces the risk of Y. And we call that rule an entailment rule. We've got 2 templates in each, template at each side. And a template is more or less just a text fragment with variables. But from now on, we'll talk about templates as based on the lexical syntactic level, which means just sub-parse trees with variables. But any kind of templates could be fit here in that manner. Probably the most important thing to note is that we need a lot of these rules. Hundreds of thousands, maybe millions of such rules in order to provide good coverage of a language. So manual acquisition is probably out of the question. We have to find some automatic way to do it. So how did people learn? Well, people were working on paraphrases until now, and entailment rules are something new. So how did people do paraphrase acquisition so far? The dominant approach was to use sentence alignment. The idea is to find 2 sentences that more or less convey the same meaning, usually based on finding shared lexical elements. And then the non-shared parts are extracted as the templates that paraphrase. If you look at the example, the 2 sentences, the clerk liked Monsieur Bovary, and the clerk was fond of Monsieur Bovary, then we can extract the template X like Y, paraphrase X is fond of Y. And now the main question is how to find these pairs of rules, of sentences. Well, so far people were using comparable corpora of many kinds in order to get some more information and some more help on finding these pairs. The first approach was to use parallel corpora, that is different translations of the same text. For example, we've seen before is Madame Bovary, translated in both translations to different translations into English. Another approach is to use comparable corpora in a way of articles appearing in different news articles appearing more or less in the same date, and that will bring you quite a lot of articles. But there's still a little bit problem of a limited resource availability. First of all, there are just not that many translations existing, parallel translations. And of course, there are many news articles that we can find today, and we can align them, and we get a lot of these. But first of all, by just aligning at a specific date, we might just lose a lot of other paraphrases that we can learn from unaligned corpora. And another thing is that we focus here only at the news domain. And so if you want to learn, for example, for the medical domain or law, perhaps this will be much more difficult to get. So this will get us really probably high precision, but might not be the only source we need in order to learn more entailment rules and paraphrases. Another approach was to look at the web as the largest corpora we have and try to learn from their paraphrases. But the problem is that we cannot just go through all the web and parse it or, well, do any kind of pre-processing. It's too big. So there was a directional approach that was taken, and that is to start with a given template, for example, X born in Y, but also to add to it some really good context that we know about it. For example, Mozart in 1756. And the point is that if we picked up the good context, for example, Mozart, well, he probably did nothing more than just being born on that date unless he was really like that genius. So if we're going to look for the web with this anchor set that we measured, this instantiation, and pick up sentences containing it, then we hope to find templates that paraphrase within these sentences. For example, we'll find X assassinate Y and Y was murdered by X as paraphrases. Again, the problem here is that we need some manual input for every template we want to learn for. Okay? And if you think about it, well, maybe for 10 or 20 templates, that's okay. But what about 200? What about 1,000? What about 10,000 templates that we want to learn for? So it's probably a bit infeasible. Furthermore, of course, for every template, there might be different meanings. Again, if you're looking at X acquire Y, we need one anchor set, probably more to get to acquisitions of companies, other for acquisition of knowledge. So there's a lot of work here. And so our goal is to provide an unsupervised large-scale acquisition of entailment relations from the web. And we need to start just with the minimal input we can, and that is just starting with the phrase, with our template, without any given context, good context. So what we'll do is we'll start with a template. We can just go through a lexicon and generate these templates. And here we have an example of X accused Y, but we can put in any kind of template we want, just not just subject, verb, object. We go into the web and collect sentences containing this template. For example, Paula Jones accused Clinton. And then we're going to extract the anchor sets appearing with that template. Paula Jones and Clinton, Sanhedrin and St. Paul. And the point here is that not all of these anchor sets are actually very good to learning. Actually, most of them are really bad because they'll add a lot of noise. And we need to do some filtering here. We'll talk about it in the next slide. Then we go back to the web, collect again anchor sets, collect again sentences as we've seen in the previous slide, and then we'll try to learn the templates that appear there that either entail or are being entailed from the input template. And the whole process can be iterated because, again, it's just unsupervised. We can take these templates and feed them in as input templates. So as we said, we're starting with the input template, going to the web, collecting sentences, and now we have to pick up the instantiations, the anchor sets from these sentences. But the problem, of course, is that not all of them are good. For example, if you look at BBC and Blair, okay, BBC might accuse Blair in some times, and other times it might praise them, and other times it just might interview them. And there are many other relations that appear with these two, with this pair. And we want to find out the pairs that capture just this, one at least, specific meaning of the input template and not others. So we need to filter out some statistical tests to be done here in order to capture what we call characteristic sets.
Are you restricting your attention to named entities as the anchors?
This is just, well, I would say coincidence, but no, we are not limiting ourselves in this work to named entities. You might get high precision with that, but again, no limitation was done here. But again, even with named entities, you have the same problem. And actually, what we did here is our test was using conditional probability. we were looking at the probability of seeing the template with the anchor set, given that we see the anchor set in the sentence. When we say if that probability is high, that means that it's not just coincidental that the template appear with that instance. It probably captures, there's some good relevance between the template and the instance. These instances, they capture the meaning of the template, and we hope they're good enough. So we'll filter up, hopefully capture just characteristic anchor sets, and then we'll go back to the web. So again, what we're looking for is characteristic anchor sets corresponding to a single meaning of the input template. Just an example of what we can learn for X prevent Y in that manner. We got things like sunscreen prevents sunburns, safety belt prevent fatalities, low cloud cover prevent measurements. This is an example for not named entities, for example. And you can see that there's a lot of variability here, and we capture a lot of things here. And think about collecting all of these manually. It's quite a hard task. So once we have anchor sets and we're going back to the web, we've collected sentences containing them, and we have to find out what are the templates there. We need to look for the template structure. And it's not that easy. For example, the template that appear in two sentences here is X called Y indictable. And it's not just the words between the two instances, and it's not even just a path in the subtree. So we need some kind of algorithm to find out the structures here. And we have a new algorithm called GSL, and we'll talk about it. First, we parse all the sentences, because we work in the syntactic level. And we're going to change back into variables all the instances. So now we've got X called Y indictable for arrestment, and finally X called Y indictable. And now we're going to look for the repeated parts, which are the templates, in the algorithm that we call GSL. In order to do that, what we do is we'll take all the sentences and collapse them into one big graph, an aggregate graph, a graph we call compact graph representation. In each node, we have the set of sentences containing that node, and the same thing for the arcs. And now we're going to look for the templates in that graph in a manner that is related to least general generalization in induced logical programming. So what we'll do is we'll start with the minimum template possible and just a path between the two variables. And then we'll look at the intersection of all the sentences appearing with all the nodes and arcs, and we'll see what other nodes and arcs could be added that contain that same set of sentences, the intersected sentences. And we'll find out that indictable could be added, but that's it. And this is most general in the way that it couldn't be, we can't find a smaller template that appears in more sentences, but it's also maximal in the size, because we cannot find a larger template that appear in the same number of sentences. That's what we call maximal most general. And since this graph contains all the sentences, there are a lot of paths between X and Y, and we'll go through all of them and try to expand each and every one of them and take out the templates that we get from them. And just another point, this works for X and Y, but also for more variables as well. Instead of looking at paths, we'll just look at spanning trees between the different variables and then try to expand them. And actually, it can work also for just one variable if you start from a minimum template that you define and then try to expand it. Examples of templates that we could learn for X prevent Y, we got things like X protect against Y, X inhibit Y, X a day keeps Y away. So there are nice paraphrases and entailment rules in here. But of course, there are some incorrect ones, which I will not show you. But let's talk about the experiment. We've ran the tease algorithm for 48 different verbs. And what we've got is yield of about 29 correct templates per verb. There's no recall measured here because really we don't know how many templates are entailed or being entailed from the input ones. We just count how many correct ones we can see on average. And we got 45% precision on average for a verb. The agreement between the annotators is about 0.78, which is substantial agreement in the kappa value. But probably one thing is important to note is that it was really, really difficult to evaluate it. It's really hard just given two templates and asking whether there's an entailment relation between them for people to actually find it out. They have to think of all the different contexts and all the different meanings of the templates and figure out if there is one context that can actually capture that entailment relation. So it was really hard work. Some related work, yeah.
So in that example, you have prevent, you had all these other verbs, and you asked if either one of them entail the other one. So here,
Either whether there's an entailment relation between X prevent Y and any of these
right? But for example, cut risk of Y.
is entailed from X prevent Y. Perhaps not vice versa, but
Right. So there's a directional.
yeah, there's a directionality which we didn't learn the directionality in this work. We just asked whether there is an entailment relation in one direction at least. Okay.
You said what's maybe difficult is that the directionality relation sometimes, for certain purposes, it's really paraphrased because it reduces heart attack and stops heart attack. Easily.
No,
Some context is not the same thing, but for all practical purposes, you want to count it as the same thing.
no, it's okay. If it's a paraphrase, that's also correct, as we
Right.
said. But
Right.
that's okay.
Depending upon the task, some tasks require exact entailment, and some tasks are more lenient about, if it's practically the same thing, it's okay or something. That's it.
I agree, and it's really hard. I mean, why vaccine is X? That's only correct when you're looking at vaccinations. I mean, prevent could be in many other ways. But
In other words, do you look at what is X and what is Y from the examples?
when we were giving, in specifically evaluating this, we gave one sentence containing the result just to get the notion of context that we found it in. So they get better ideas. But it still was really, really hard. You need to give a little bit more context, like whatever for example, if you find X prevent Y in that same context, it would be good to give two sentences, the two sentences so people can actually see them and try to evaluate.
So do you
It's
think
hard.
that this methodology overstates the precision then?
Understates, actually.
Understates.
Understates because people miss a lot of correct ones. And
Did you have a window beyond X and Y that you were looking at? I noticed X a day keeps Y away, which is normally something or other keeps the doctor away rather than the disease. But
this one says aspirin a day keeps heart attack away.
but you have to look beyond. Aspirin prevents heart attack. You have to look beyond that window of the two entities that the two nouns that you are using to.
You should.
frame this.
This doesn't mean. There's definitely, as you've seen, that precision was 45%. So it's not the perfect method. And obviously, the longer you look and the better you get the aligned sentences, you get better results. This is more just looking. And actually, what we did, and I probably didn't mention it. I'll just show it again here. If you see, there's the C down there that I added. When we picked up anchor sets, we didn't just pick up the X and Ys where they appear, the instantiations. We tried to look for another word or phrase that capture more or less, help capturing the specific meaning of that template or that event. In order that when we look for other sentences, we'll look for all of these three together in order to capture the event better. For example, if we could pick up, I don't know, a date or something like that, and we just look for sentences containing that date, it would be good. In many times, we couldn't find one good additional context. In several, we could. And we usually found out that if you pick just two more contexts, it's just getting too specific, and we couldn't find almost any sentence at all containing it. So you have to decide which is the best one to pick. Sometimes there's none. Okay, so
When we try to apply this knowledge, acquired paraphrase, acquired entailment, then you want to have the restriction for X. In this pattern, X has to be disease name, Y has to be.
could be. That's a good question. The question is whether if you're going to use something that is not in the right context, but you know what are the types that you're looking for, perhaps you won't have any problem at all, because if you already start with the type, it really depends of what the task is. I'll talk about it in a minute when we're using it in relation extraction. If you already know what the types that you're looking for, then you're limiting yourself already in a different way. And then you have no problems of using everything, because only the things that actually fit into that types will appear in what you're looking for.
At the beginning, you said that there is a problem, two problems, entailment and one sense disambiguation. Well, that sense, prevent can have different senses.
Yes.
So one sense can be used on.
Exactly, and I learn prevent in many senses. And what I say that I can use that, for example, in the textual entailment, in the recognizing textual entailment challenge, I can use everything because if all the text and hypotheses are coherent, you just won't see companies in A a day keep Y away. It just doesn't happen. So if you see X prevent Y and X a day keep Y away in the same with the same instantiations, then these are good contexts, unless someone deliberately went and generated bad context for you, just arbitrary garbage, which happens on the web, by the way. There's a specific site I can show people just generate junk sentences which are correct syntactically. Very bad, yeah. Aside of that, we hope that most context is pretty good. So as we said, it was really hard to evaluate it, and we will look for another approach, and we'll talk about it later on. Compared to other algorithms that provide unsupervised acquisition, first we've got the DIRT algorithm by Lin and Pantel, which is not using aligned sentences. Instead, they were looking at distributional similarity. They were looking at all the nouns appearing at the X side of a template and all the nouns appearing at the Y side and creating two feature vectors, and then comparing these two feature vectors to other feature vectors of different templates and aligning that way. Since the features in each feature vector are simple, then there's less of a sparseness problem instead of looking of like X and Y together. Sorry. But since you decouple between the X and Y and just put them in two sets without remembering which relates to which, then the precision is a little bit lower. And I'll show it in the next slide. Another work, Satoshi's work in 2005, was done also in an unsupervised way on a non-comparable corpus. And here it was focused only on named entity pairs. A nice thing that was done in order to overcome the sparseness problem is to look at the template structures and look for keywords that happen in two templates and say that if the keyword appears in these two templates, they are immediately paraphrases without looking at the context. For example, if you have X acquired Y and Y acquired by X, they are immediately paraphrases just because we have acquire in both of them. And that's a way to overcome sparseness. Of course, there's a problem to find out the correct keyword. There are different algorithms. When we compared our results to the DIRT algorithm data set, we picked up about 20 verbs, looked at what we've learned compared to what DIRT learned. And what we've got is that we have more or less the same yield. DIRT does a little bit better, but we did almost 20% more in precision, and that's actually statistically significant in what we measured. Again, it was really hard to evaluate it. But one thing we've noted is that Tease and DIRT more or less complement each other in terms of what they learn. Because DIRT learns from a specific news domain corpora, so they learn pretty good results for the news domain, while Tease is looking on the web, so he learns all kinds of templates for all kinds of domains. So there are really nice differences there. Again, as I said, it was difficult to evaluate, just looking at two templates, and we try and handle that. So,
can you go back to that slide before? When you were measuring precision, what do you use to determine where you terminate your search?
We've took everything we've learned and everything DIRT learned, and just
so you don't
look.
Have a threshold?
No. How would you set the threshold?
I don't know. I was just curious.
This is somewhere. I mean, I can tell you how we ranked things. We've just looked at how many anchor sets appear both with the input template and the learned template, and we'll say that's our score. It's like 5 different anchor sets, we'll give it 5. 10 different anchor sets, we'll give it 10. And we rank it that way. DIRT has its similarity ranking, but is 0.01 much better than 0.05? Is 0.2 better than 0.5 in another in another template. I mean, the numbers are not even comparable. It's really hard. So we just looked at everything. And anyway, unless you know how to cut it, you want to use everything. I mean, if someone will tell me you always cut here, then previously you would just cut the data set and provide me only what's interested in. So that's for everything. So again, as I said, we've seen the entailment framework, and we're armed with some acquisition method. Let's take a look at what we can do it in the NLP tasks. Let's focus on relation extraction. And again, that's a paper in EACL 2006, together with Lorenzo Romano, Milen Kuilakov, and Alberto Lavelli. So what is relation extraction? It's a subfield of information extraction where we want to identify the different ways where a target relation is expressed in documents. For example, we're looking for mergers and acquisitions. We would like to find pairs of companies that one acquire the other, protein interactions, management succession. There are many relations. And traditionally, it's performed in a supervised way. And we need dozens, probably hundreds of examples in order to train a classifier. And we need these examples to capture the different variability that appear with that relation in order to learn to capture good variability. So as we said, it's probably feasible for 10 templates, maybe 20, but about 100, 1,000, 10,000 templates. It's getting too costly to annotate everything. And there's just little work on unsupervised approaches until now. And we're thinking, well, maybe we can fit in textual entailment into that problem. Because we could say, well, if we have candidate pairs for a relation between them, we can just put it in with our input, our target template, and ask whether the text entails the target template instantiated with these two entities. So our goal is to provide an entailment approach for relation extraction. And from one side, we want to get an unsupervised relation extraction system. And on the other hand, we want to provide an evaluation framework for entailment rule acquisition, which we hope will be more objective and better than what we've seen so far. Okay? So let's take a look at our approach. We'll start with an input template describing the relation that we're looking for. We're going to use an entailment rule acquisition to learn templates that should entail the input template. And then we're going to use a syntactic matcher in order to find these templates in the document and extract the different instances. Now, how does it solve our goals? Well, if we have an unsupervised relation extraction entailment rule acquisition, then we have an unsupervised relation extraction system. And if we have two of these algorithms, we can just replace them and measure recall and precision on an annotated data set for relation extraction, for example. And then we can actually see better which is doing better than the other one. And another thing is that you can think about this as a kind of entailment engine, which is just a basic one. But we have the syntactic matcher, which is performing the inference. We'll talk about what is a syntactic matcher. And we have the acquisition, which provides us a knowledge base of rules. In this paper, we've used T's as the algorithm and used transformation rules for implementing a syntactic matcher. We'll talk about it. So let's think about finding X prevent Y in this sentence, sunscreen which prevents moles and sunburns, etc. There are two syntactic phenomena that prevent us from directly match that template. One, there's an apposition, a relative clause, sunscreen which prevents, and then there's a conjunction, and sunburns. And we need to handle these two phenomena in order to match the template. So we need a syntactic matcher that should handle different syntactic phenomena. And as I said, our approach is transformation rules. I'll give an example. We have the parsed sentence on the right and our template on the left. And it's easy to find prevent. And now we're looking for the object. And we're going to use a rule that says, well, if there's a relation and a conjunction, we can apply directly the relation to the conjuncted noun. And we'll find sunburns as the object. And the same way, we can find another rule that will find our subject. So what are the phenomena that we handle in this paper? What rules do we have? We have rules for passive and oppositions and conjunctions and relative clauses, but also less known is transparent heads, for example. What is a transparent head? It's the head of a syntactic noun phrase, which is not the semantic head of that phrase. For example, here we have fragment of y. Fragment is a transparent head because it's the head of the syntactic head of that phrase, but it's not a semantic one. Y is a semantic one. And when we match x activate y, we want to capture y as the instantiation and not fragment. Okay? So we have rules for that as well. We did our experiment on recognizing interactions data set, protein interaction data set, UNESCO 2005. It contains 200 Medline abstracts, annotated, gold standard. And we use just one input template, x interact with y. That's it. That's all we need. We're completely unsupervised. We've split the data set into development and test set so we can provide some manual analysis before we actually run it on a test set to see some interesting things. First of all, we're actually looking to assess the whole approach, the template approach. Maybe it just matches 20% of the cases, and then it's not really interesting. Another thing is to try and figure out what's the potential recall of the tease algorithm, assuming that we have a perfect syntactic matcher. And that will give us kind of an upper bound of what we can get with the syntactic matcher as well. And finally, looking at the distribution of these different syntactic phenomena that we've handled. So what we did, we went through any sentence annotated with protein interaction, and we marked whether there's a template that could be used to identify these two proteins as interacting. And also, we annotated the different syntactic phenomena that appear here and should be handled before we can actually match the template. So for example, here we have the template x associate with y. But there are two phenomena. There's apposition and relative clause. The apposition is ICDI1, comma. It goes here. And then the relative clause, phosphatase that associates with CDK2. And once we handle these two, we can actually find x associate with y and extract ICDI1 and CDK2 as interacting. We did that to all the sentences in the development set. And let's see what we come up with. First of all, 93 of all the interacting pairs can be found using templates. That's really great. Okay, that's almost everything. And we're very happy to know that. The rest where you usually need a discourse analysis or some logical inference, but just only a small part of them. Some of the most frequent templates are, of course, x interact with y, but then x bind to y, association of x with y. But there's a lot of variability here. Another thing to note is that within these 93%, we need just 21 different, lexically different, of course, because there's a syntactic, if you think about the syntactic matcher, it provides a kind of syntactic closure for each template. So we just need to learn one lexical syntactic representative to get all the different syntactic variations. So we need 21 different lexical syntactic templates to get up to 50% recall within these 93%. But we need 175 different templates to get to 100. That's a lot. So now we have to compromise because it would be very difficult to get to 175, but maybe not that hard to get to 21, maybe 6, well, to 50, maybe to 60% recall. Finally, what we saw is that transparent head, which is seldom mentioned in literature, appears in about a third of all the cases, of all the interacting cases. That's a lot. And that's, again, something that people rather ignored or, well, didn't consider adding into their systems, maybe. And then it followed by appositions and conjunctions, which is appearing about 25% of the times. So transparent heads, for us, is very encouraging. This is a new thing to research how to handle these in a robust way. We ran T's on X interact with Y. And what we've got, well, this is the list. Again, you can see nice variability. X activate Y, X stimulate Y, X recruit Y. And these are only the ones that match, of course, proteins. There are also ones that, things like X talk with Y, which appears between people, but not interesting for us. And since we know that we're looking only for proteins, if we match whatever we learned, just the ones that actually can work within proteins will come up. So that's at least one answer for you, Satoshi, in that case, at least.
Did you filter out the incorrect
No.
ones before you used
Everything is put in. So we didn't filter out. And this is a way to measure more or less the real precision if you think of such algorithms. If you learn junk, they're incorrect, but they'll never match anything useful. So you don't care in that way. as we said, we measured the potential recall on the development set of the tease algorithm. First, we looked at we used just what we've learned for the input template, and we got to 39% recall. That's real recall, not within 93%. And then, using the iterative mode, we picked up the top 5 ranked templates and added them in and learned more templates, and we got 10% more on recall. And finally, if we had the perfect morphological derivation, and I'll show what I mean with that, we can get up to 63%. So again, as we've looked at the syntactic matcher, which is something we can develop as a generic way to cover all different templates, we can use also a morphological engine, which can take a template and generate the morphologically related templates from it. For example, if you have X interact with Y, you can generate X interaction with Y, or X interaction between X and Y, and things like that. We think that we can create such an engine. We're actually working on it right now. We didn't have one prepared for this paper, but we were developing one, and we'll see. And as we can see, it should add quite a lot of recall. So we're very enthusiastic about it. So just to demonstrate it on the most frequent templates that appear in the development set, the green ones are the ones that can be covered just by using the input template. If we use the iterative one, we can just capture one more template. And using the morphological one, we can capture almost everything this side of X form complex with Y. So as we said, association of X with Y come out from X associate with Y using a morphological derivation.
The recall is because the recall is 63%, so there is a long tail which...
Yes, there is a long tail. As I said, there's 175 different templates that we should cover. So the tail is very long. So 63%.
How many did you find?
How many templates there are? Actually, I don't know. I don't know how many did we cover. It's a good question, whether we covered a lot in the tail or just up in the top. As you saw, we covered almost all the most frequent ones, but there are a lot of in the tails. But actually, there are other ways to generalize and create other such derivation engines that will create more templates automatically, quite easily, maybe.
So it's nice to see what...
Exactly. There's a lot of work to look at the tail and see what kind of linguistic phenomena appears there. And it's a good thing to look for. So finally, not everything is perfect. When you run the system on the test set, we just got 18% recall just using the input template, and using the iterative mode, we could get to 29%. And of course, we didn't have a morphological engine back then, so there's no number to put there. Some problems that we had, dependency parser, of course, make a lot of mistakes. So once there's a mistake, we can't match anything. There are probably some syntactic phenomena we missed, some bugs in the program, things like that. And of course, precision is going down as long as we're using more and more templates, because T's precision, as we've seen, is not 100%. When we compare ourselves to supervised approaches, the two state-of-the-art approaches are Bunesco 2005 and Giuliano 2006. They were using SVM, and they were running on 10 cross, I think it was 10-fold cross-validation on that data set. That means they're using almost all the 200 abstracts to learn in order to cover what they got. We have the two blue dot lines here, two blue dots here, and we're not there yet, but we're not that far. And this is just our first chance, our first attempt. And we know that there's so much to improve, and we're already working on it. And well, we hope that next year we'll do much better than that and try to get closer and closer to the green and red line. We're very encouraged. Some related work. Again, Satoshi, yeah. A paper in the ACL providing open domain relation extraction. The idea here is not to start with a given template, but a description of a scenario, and then learn the templates that relate to that scenario, and then learn paraphrases for these templates and try to match them. Perhaps one important thing here is that there was the direct matching of the templates that were learned and not using a syntactic matcher. So that's one difference. Finally, conclusions. We've seen the textual entailment paradigm, which is a text-to-text mapping framework for applied semantics. We've seen the tease algorithm, which is an unsupervised web-based acquisition of entailment rules. And we've seen an evaluation of these in an application eyes or glasses, and we get to almost 63% potential recall. Of course, only a protein data set, but hopefully it extrapolates to other data sets. And we think it's an encouraging unsupervised performance. And we also seen an unsupervised domain-independent relation extraction approach using textual entailment. We can get to 93% of at least potential coverage of the instances, again, only for protein interaction, but hopefully it extrapolates well to other domains. Since there's no additional training needed, we can just try it on other data sets, and actually that's what we're doing right now. And this is also an evaluation framework that we're working on for evaluating different acquisition algorithms and comparing the results. For future work, we're going to work on improving our syntactic matcher, as said, adding morphological derivation, but also trying to acquire and learn the rules. We're going to try and improve these first by using a syntactic matcher as part of the learning to overcome some of the sparseness problem. We're going to use some probabilistic, we're working on trying to find out some probabilistic estimation to find the directional relation. And then finally, as I said, since there's no annotation needed for any other domain, we'll just run it on other data sets and see the result. To end up with two open questions, are knowledge and training data more important than inference or matching methods? Or perhaps, given more knowledge and training data, the difference between inference methods will become more apparent. Thank you.
I was a bit surprised. I mean, the earlier example you showed that somebody got shot, and then you may not have certainty to say that he died. So this kind of relationship, of course, can be modeled probabilistically, right? So there's a chance, but I mean, depending on how seriously he's shot, you can infer, how likely it is. So why isn't the mechanism built into?
So we do expect to have, first of all, the whole notion of textual entailment, because, as we said, most likely true, there is a probabilistic notion to it.
Yeah, but
that's one thing.
Built into anything that you're talking
It should be, because I was talking about learning rules, but then, as I mentioned, we're actually working right now on providing some kind of probabilistic framework for identifying the correctness of these rules and the directionality of these rules. So it's true, actually, that you want to provide probability, not just ranking or something like that. But it's hard.
Somehow human has to label, training data has to be labeled somehow. Like, if you have some word like, serious, gravely, or something, then the chance will be higher, and the human provide the information to begin with. So is that the requirement that in order to make that mechanism work?
I'm not sure. I don't know. I mean, I'm working on it. I will tell you, in a year or so.
The artificiality of the task where you have two short text segments where it may truly be ambiguous, where in running text, the answer as to whether the person died or not may be clear, right? But you're pulling out small snippets.
Yes.
I mean,
have the full understanding the whole thing is kind of.
And there are many approaches, by the way. And there are many other approaches for learning paraphrases. This approach was used, and the approaches are demonstrated by using contexts in order to find paraphrases. You can use other linguistic hints to find other, maybe more directional relations, such as if you find something after something else, you might say that one entails the other, but not vice versa, things like that. But still, it's just ongoing work.